Hello and welcome to Waka Waka Breaking It Down. This is the kind of the second investigation on logarithms, I believe. So you should have had one activity already, and then also the warm up. In the warm up video I make, there's some good explanation about what a logarithm and how an exponential function and a logarithm function are inverses of each other. I'll talk about that here as well, though. So this is just a kind of more investigation. And logarithms are one of those things you just have to play around with a little bit for a while before you kind of get used to what they really mean and what's going on there. So don't be afraid to just jump right in and do your best, and it'll start to all come together if you keep playing around with it. If you give up, of course, it won't. So don't give up. All right, so let's go. We're starting off with an exponential here, and then on problem two, we'll get to the inverse of it, which is the logarithm. So this is just 2 to the x. So we're putting in x values starting from -4 all the way to 4. 2 to the -4. Remember the negative, when it's an exponent, will inverse it, right? So it'll flip it over. And then, of course, 2 to the fourth power is 16. So 2 to the third is 8, but since it's a negative exponent, it flips over. So 1/8, and then etc., right? 1/4, 1/2. 2 to the 0 power is always 1. No matter what it is, to the 0 power is always 1. And then, of course, 2 and 2 squared and 2 to the third and 2 to the fourth. So hopefully you can fill that chart in, no problem. Once you have that, you can graph the black equation that we have here, right? So 2 to the 0 is 1, 2 to the first is 2, 2 to the second is 4, 2 to the third is 8, right? Etc. all the way to 16. And going the other way, if I were to put in a -1, you can see here on the bottom left, if I put in a -1, 2 to the -1 is 1/2. 2 to the -2 is -1/4, right? And it keeps going, or sorry, it's just 1/4, 1/2, 1/4, and then it goes 1/8, 1/16, 1/32, and it gets closer and closer to 0, but never quite touches it, right? 1/64, 1/128th, right? So closer and closer. So that's why we say that y equals 0 is the asymptote. That is where your exponential will approach, but it'll never cross. All right, now if you go down to problem two, it says let's draw the inverse of that. Well, when I don't have an equation, which I could just write it, but let's take a look at it just purely graphically first. So if I were to draw in the y equals x line right through the middle here, right? Remember, we always said inverses are, you switch the x and the y when you do an inverse. So if I have some equation, 2x equals y, let's say, and I'll put this all together like algebraically and graphically and put that all together here, right? And numerically with a table. Okay, so this is my original equation, the black equation that I have over there. So if I want to do the inverse of that, remember we switched the x and y. That's what we said. So it becomes this, right? That's what a logarithm is now. So if I solve this for y, it's going to become the logarithm that we're talking about. Let's look at the graph first, though. So let's say this point right here, that's the 0.38, right? 2 to the third power is 8. Okay, so the inverse of that, I have to switch my x and y's, just like I did in my equation. I switched my x and y's. So now the point I'm graphing is 8, 3. Right there, right? So this point right here is 8, 3. So hopefully that makes sense, and I could do the same with all these. This is 2, 4, so I would graph 4, 2. This is 1, 2, so I would graph 2, 1 for the inverse. This is 0, 1, so I graph 1, 0 for the inverse. And that's true for the half as well, -1 half. So instead I go half and then go -1, etc., etc. And since these values approach the y equals 0, all these green values are going to approach when x equals 0. So we're going to find that x equals 0 is the asymptote for a regular logarithm. Now, of course, later on, we're going to shift things around, so the asymptote is going to move. But for now, when you have a basic log, the asymptote is x equals 0. just like a basic exponential, you have y equals 0. Okay, let's go back over to the algebra part. So how does this turn into a logarithm? Well, since we have a base 2, what you do to solve for y is you do the log of both sides with a base 2. If it was some other base, then that's the base I would use in my logarithm. So I'm going to use log base 2 of both sides of the equation. I'm trying to write it out nicely so it seems kind of slow here. So I'm doing the log of the left, base 2, log of the right, base 2. Dun, 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 dun. Sorry, going a little slow here. Here we go. And there's x. Okay, so when I did the log of both sides, on the left-hand side, if I have a base 2 of a base 2 exponential, those are inverses, I know. They cancel each other out, and this will just become y. And I talked about in the warm-up video and probably some other videos as well. So now you can see when I simplify this that y equals log base 2 of x. That's the inverse of y equals 2 to the x. So that is the inverse of this. Right? So that's algebraically how you'd solve it. Graphically, you're reflecting over the y equals x line. Right there we got y equals x, right? So you reflect over that line to get an inverse. You switch the x and y's. You can do that with the points, right? So on a table, when you looked up above, all those points I had in the table, right, 3, 8, and 2, 4, etc., you're just switching the x and y values to get your inverse, Okay, so everything just switches. Right there is a beautiful kind of summary of everything all together, graphical and algebraically what's going on, and also thinking about the table of values. Sorry, I'm gonna start. I have to erase all these things now. Here we go. Erase, 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 and then we'll move down and go a little faster now. I wanted to take it nice and easy right there because that's like everything in once. So hopefully you can understand that. Okay, so number 2 we did. You get that? Yes, it's a logarithm. So we did number 3 as well. I switched the x and y's, right? And I solved for the y to get log base 2. So I did number 3 already. So number 4, we start to practice a little bit. So how do I use this idea to solve equations? Well, you just take the logarithm on both sides. It doesn't matter what this number is over here. You can just take the log of it and throw it in your calculator and you're good to go. The only thing you have to really pay attention to is what the base is over here, because that's the logarithm you want to use to undo that exponential. So if this is log base 2, I need to do the log base 2 of both sides. When I do the log base 2 of the right-hand side, the x is just going to drop out. And then I do the log base 2 of the other side, and that becomes my answer. Let's take a quick look at the calculator. I'm going to insert a calculator page here for us. And remember, right on the left-hand side above the 10 to the x is a log button. So we're going to do control and then hit that, and you'll see it gives you the option to put in whatever base you need. We need the log base 2, and I want to put in 31.6. 31.6. And you get 4.98. So there's your answer, right? It's once you get used to it, it's really easy and it's really useful. I mean, to solve for an exponential, remember we had to graph these out and look for the intersection? What a pain in the tuchus. Now we can do it really quickly, right? Okay, so I'm looking for my exponential. I'm on part B here. So looking for my exponential, looking at the base, that's 8.4. So when I do the logarithm of both sides, that's the base I want to use. And I know it feels a little weird as a decimal, but it doesn't matter what that number is. It can be a decimal or not, or be a whole number or a decimal, right? It doesn't matter. So we do the log of the left-hand side. When you do the log of this, the x is just going to drop out because they're inverses of each other. And if you need to see what that looks like, I'll just write it out once, but you're doing log base 8.4. Like some of you really maybe need to write this out every time until you get used to it. But you can tell after a while we don't really even write that anymore. We just this is what the left-hand side is looking like, right? And then the log base 8.4 of an 8.4 base of an exponent or an exponential. right? Those are going to be inverses. So the x just drops out, right? So we don't even write it usually because I know that's what I'm doing, and the x is just going to drop out. Just make sure it's the same, sorry, the same log on the other side. Okay, again, just throw that in your calculator. Log base 8.4. I can just copy paste this down, change the numbers, 8.4. And then this is 2340. And there you go, 3.645, right? That's my answer. Okay, when you get something a little more complicated, like sometimes there's a number in front of the exponential that's being multiplied, or sometimes, like in this case, you have something added. You need to get rid of that first. You need to kind of get your exponential by itself first. So in this case, we subtract 5 from both sides, right? Subtract 5, and you'll get the next line, right? Where we have 3 to the x by itself now equals 12. Now I can do the logarithm of both sides. So again, 3 is the base. That's the type of logarithm I want to use on both sides. When I do it on the left, they become inverses and you just get x out of it. When I do it to the right, it looks like that. Just remember, there are technically parentheses here, even though we tend to not write them a lot, but there really are parentheses there. So log base 3 of 12, and you just throw that in your calculator, you get 2.26, just like we did here, right? Just throw it in. So I've done that a couple times, so I'm just saving time. I'm going to keep going. Okay, so what's kind of the rule, right? What are inverses? Well, if you have b to the x as your function, the inverse of that, and you can see down here we have the inverse notation, the inverse of that is a log with the same base, b. Whatever this b is, then your log should have the same base, and they will be inverses. So that's your toolkitting. Number 5, more practice. But in this case, we just want to solve for the inverse. We're solving for an inverse. So normally this is y equals, right? With our function notation. We switch the x and the y's. So we're not really solving. Sorry, I misspoke. But we're just reversing things to find the inverse, right? So we switch the x and the y. Then we're trying to solve for y, right? So we subtract 2 from both sides first. Get your x minus 2 over there. And then just like when we were solving, I'm trying to get the exponential part by itself first on one side of this equation, right? So I get the 3 to the y by itself. That's when you can do the logarithm of both sides. Well, which logarithm should I use? Well, whatever this base is, that's the base you want to use in your logarithm. Remember I said there's parentheses after the log? Well, this is a good reason why. This whole x minus 2 has to kind of stay together as a group. You're not just doing log of x only, or you're not distributing the log or nothing like that. It's just log base 3 of the whole thing. You just leave it like that. Don't try to do like log of the x minus log of the 2. You can't do that. This log does not distribute, okay? Don't do that. All right, so there you go. You've solved for y. Why did the y drop out? Oh, because we did log base 3 of a 3 exponential, right? Those are inverses, and they're going to drop out, and the y is going to come down by itself. Those are going to cancel each other off. Okay, so that's the y it looks the way it looks right there. All that we have to do now maybe is change the y into inverse function notation, which is what we want you to do. It makes it look nice and proper, and it really explains more. If I just have y, it's not very clear how special that is. But if I put inverse function notation, it tells me, hey, if this is f, this is the inverse of f. So it's more specific. It gives me more information, tells your reader exactly what's going on. So we like that a lot better. So please do it. Okay, so yeah, you're just rearranging. So here's some more practice, some different situations. So part B, we have an exponential, but in this case, you see how we have 3 to the x up there? It's still part of the power, so don't let it throw you. Just do log base 4 of both sides, because 4 is still the base. So we do log base 4 of the left, and you get that. You do log base 4 of the right, and the 3y drops out. Remember, this 3y used to be the power, so whatever's in the power is going to drop down. And then to get y by itself, you just have to divide by 3 then, right? So it just, this little weird situation just added one more extra step where we have to divide by 3 at the end, and then you can change your y into inverse notation. Okay? It worked just like the other one though, right? It works just like the other one. Okay, part C. What's different about this? Well, the only thing different now is that we're starting with the log, and we're calling that our function. So you can see down here when we get done and we have our inverse, it's going to be in the exponential form. So we're kind of going backwards, we're just starting with the logarithm and ending with an exponential. Oh, well, how do I get rid of a log, Mr. Waka? Well, you do what we call roll the log. It's kind of like when we solved for a value before. So let's change this to y. Okay, you switch your x and y's, which we did down here. Then we do what you call roll the log. So we're going to take this base of the logarithm, we're going to raise it to this power, which is x in this case, and then that's going to equal what's inside the logarithm. And because we do this circular motion, we call that rolling the log, and to get rid of a log. Now, why does that work? Let me do a little side note real quick. So if I put a 3 here and I had a log base 2, and I said this was equal to some variable, you'd have to ask me, I'd have to ask you, like, what does y equal? You'd have to say 8. And just the way the logs work, because 2 to the third power is equal to 8. So this is kind of what's going on when you look at a logarithm. This is the base of your exponential. This is the power of your exponential. And then this is the answer of your exponential, like what it equals. So if I had 2 to the, whoops, it's a weird 2. 2 to the third power equals 8, right? These two things are the same, just in different forms, right? They're kind of in inverse forms of each other. That's what you're really trying to get used to in this unit. So if you can understand that, then the rest becomes a lot easier. Okay, so we did the log of both sides with the base 2. Or sorry, we rolled the log. We didn't do the log. We rolled the log to get rid of the log, right? So 2 to the x power, you can see that down here, equals whatever's inside, in this case, y minus 3. We're still trying to get y by itself, so you add 3 to both sides, and there you go. That's your equation. All you have to do is change y into inverse notation to really show the reader that you have found the inverse of what we started with, h of x. Okay, it's an exponential, right? But look, we got the shifting going on now, don't we? We're going to get to that later, I'm sure. All right, number 6, composites. This is kind of what we've already talked about, so this will go very fast. We've already shown that when you do a composite, like we proved, if we want to prove something is an inverse, we just put one into the other. And it doesn't matter if I put the 5 to the x into the log. Those are going to be inverses. You'll just get x. I could actually put the log into the 5 to the x. And either way you look at it, I know this looks really goofy, but any way you look at it, they are inverses of each other, and you will get an x out of that. It'll just equal x. They're inverses, and that's why that works, right? So if we want to try to show these are inverses or not, or if we just want to do a composite because they told us to, right? This particular notation tells us to take s of x and stick it inside of r. The little open circle O right here, the circle that you see, that means of. So it's like do r of s of x. So r of s of x. It's the same thing as saying r of s of x. That's the same thing. Okay, so we're going to put s into r. That's what they told us to do, not the other way around. So I got to take s, stick it inside of r. What does that mean? Well, it means wherever you see an x over here, I'm going to replace it with the whole s. So that x comes out and all of this goes in. Okay, so you're going to see that. So we got log of, right? Log of, and this isn't written as base 10, right? But if it's not shown, then we always assume it is base 10 every time. So that's log base 10. Okay, great. I rewrote that. And then I'm putting this inside. Okay, I did that. Check. And then whatever's left over, you just continue writing it out. Okay, plus 5. So you're just replacing that in. And then we try to simplify. I can see log base 10 of an exponential base 10 are inverses. So that whole thing just becomes 2x. Okay, it just drops out. And then the plus 5 is just hanging out waiting for you to finish. All right, that's what we get. We don't get x, so I've kind of proven that they are not inverses of each other, but I can still do the composite and simplify it, right? Ooh, okay, something new. This is working with e a little bit. We've already seen e to the x. We've already worked with that for continuous compounding. What's the inverse of an e? Well, we made up a special base. We made up one with a log base e. Like in this case, I could just switch the x and y like we normally do, take the log of both sides like I always do, right? What I always do. When I do that, though, I am going to use the e as my base of my log because that was the base of my exponential. So when I do that, you get this log base e. Now, we haven't defined it yet, so this is maybe the first time you're seeing this, but we call this the natural log. Like you can see it down here, natural log, right? And we use this ln to represent that. It's very special. Just like if I just had a log with nothing there, I would think it was log base 10. But if you see ln of x, I'm going to know immediately it's a log base e. It's a special log. It's on the calculator. Let me show you that. So if I pop over here, you see we had the log over here on the left, and right next to it is ln, and obviously that's right above where the e button is. They're not dumb, right? They know what they're doing. That e to the x and the ln go together, right? So let's just prove it to you real quick. What if I did e to the x and I put in, I don't know, 3.6, right? That gives me some number. But now let's say, whoops, let me, sorry, let me do the natural log of that. So I'm going to do control and then natural log, and I'm going to copy paste that down in there. You see how I have set up with inverses now? So the natural log of an e. And if you hit that, it's just going to give you whatever you put in the power because the computer knows they're inverses of each other, right? So it doesn't matter what you put in there. It's just going to pop right back out. All right. So they're inverses each other. I could do it the other way. Let's do e raised to the natural log of 3.6. Ooh, that's backwards. What's happening now? Oh, they're still just inverses. No big deal. Okay. So it's just like logarithms, right? You can try this with any log or any natural log. It'll always be inverses of each other. So it's just a special case, something we're just another thing to get used to, okay? All right, so why does that help? Well, when we give you those population equations, right, with bacteria growth or the population of a country or something like that, or maybe you're saving money and we have continuous compounding, you're going to get an equation that has e in it, right? Because we do continuous compounding. So to undo that and to solve for some time, right? You see how we have x in the exponent? To solve for that, I don't have to graph anymore like we did in the previous unit. I just have to solve. So in this case, to solve this, I'm going to try to you need to get the exponent part by itself first. So I'm going to divide by 334 first. And by the way, I hope you were able to kind of write out the equation to start with, right? We started with 334 million. We have a 6% growth rate, but they say it's a continuous growth, and that's why we're using E, right? And then we end up with 400 million, but we want to know how long that took, right? Okay, so that's what we're solving. So divide by 334, get the exponential by itself. And then to undo that exponential, we use logarithms. So in this case, I'm going to do the natural log of both sides because it's the log base E of both sides. When I do that, the left-hand side just looks like it's shown here, right? You did the natural log of it. The right-hand side, I'm just doing the natural log of this whole thing. And when I do that, they're inverses of each other, just like I showed you on the calculator. So whatever in the exponent is just going to drop out. And that's why you have this just sitting here. 0.006x. Okay. All right. So this is just something you throw in your calculator. Natural log of 400 over 334. 400 divided by 334, right? 0.18, right? So that's what I got here. Sweet. And then I can divide by 0.006. Okay, let's divide that by 0.006 and I get 30. Okay, sweet, 30. So it took 30 years. So X is in years. R was my rate, right? My 0.6%. It's really small percentage. That's why we have so many decimals on it. So this was 30 years, right? It took 30 years for this to go from 334 million to 400 million. Okay, isn't that way easier than trying to graph it and look for the intersection? I think so. All right, you got data. Now this is teaching you how to use your TI Inspire a little bit. I went ahead and put this data into a spreadsheet so I could work with it and show you. So you're going to have to go to your plus page. So on your calculator, right above the doc, you see how it says plus page? So you can do control and then plus page. This isn't going to work in Scratchpad. It's not going to work. You got to go to a document. So if you're not familiar with that, you can go to, you hit the home button, right? And home number one. If you hit home number one, you'll get this menu and you can add a list in the spreadsheet. Okay, so you just open that up. Okay, and then you can name it at the top, way up here, name the columns, and then start putting in your data. And you'll see that I did here on a different document, I did that. So here's what I did. I put decade and years. You can name it whatever you want. You just don't name it X and Y. The computer gets confused when you say X and Y because it's using X and Y as variables. So you can't do that. And then just put in those values they gave you, right? So this whole table. Okay, so pause if you need to, and then I'm going to continue. All right, so they want us to graph it out, and then we're going to find this. We're going to find this regression equation. So it goes pretty fast. Again, I'm going to have to go to plus page. I'm going to add in a page, and the one I'm going to add in is a data and statistics page. Okay, so I do that, and you'll see some points are there. You have to tell the computer what variable goes on the x-axis and which goes on the y. So down here, you just slide your cursor over. Just use your mouse pad, then come over here and click on the bottom, and you'll see it'll pop up. Oh, I forgot. Which one do I want? I think I want years on the bottom. And you'll notice that I used this as my 0. No, what did I say? They said this was 1, I think. So this became 1 and this was 2. Like how many decades since it says since 1890. Sorry, this is where I'm looking, right down here. So since 1890. So they tell us that x equals 1 has to be 1900. So I made this 1, right? So let me go back to the spreadsheet here. You'll notice how I put 1 in there. I didn't put 1900. I just put 1. All right, 1, 2, 3, 4, 5 for decades. So this is 1900, 1910, 1920, 1930. All right, I just have to remember that when I'm doing it. Oh, why did I put years over here? This should be like, oh yeah, it's life expectancy, but in years. Okay, so this is decades time-wise, and this is years for life expectancy. That's what I have. Okay, so I want to put decade down here because that's how many decades have gone by. And then I'm going to put years over here for my life expectancy. So if you need to pause to catch up, then please do so. But this is kind of what you should end up with, something like that. Okay? All right. If you're caught up, I'm going to move on and do the regression. So in your calculator, on your calculator, just hit the menu button. When you hit the menu button, this will pop up. And under Analyze, we have a regression place here, and you can try to make different types of regressions. If I tried to do an exponential, let's say, like it's probably not going to work because remember exponentials go up. If I try to do linear, that's not going to work because my data it looks curved, right? It doesn't look linear. So what do I have here? You're supposed to kind of recognize the shape of your data. Like just look at this data, how it goes like this, right? that should look to you like a logarithm. So when I do my analysis regression, I'm going to be looking for this logarithm down here.